Welcome back to Honors Calculus. In this video, I want to look at problem solving with density. The idea of density is one that you should be familiar with from even a basic understanding of science. Typically, when we talk about density, we are talking about density of mass. So the density of an object, let's try using a thinner pen, is the mass divided by the volume. And there are some typical applications that are taught in basic physics classes or even middle school physical science classes. An object that is more dense will sink in a liquid that is less dense but will float if the other is true, right? Uh, Copper is more dense than water, so a penny sinks if you put it in a glass of water. Styrofoam is less dense than water, so a styrofoam peanut floats if you put it in a glass of water. But that's not the only place we can talk about density. We can also talk about a charge density. How tightly are the electrons packed in something that is statically charged? Or how tightly are the electrons packed in a wire where current is flowing? We can talk about a population density. How tightly packed are the people in a place? We can talk about some things that are a lot more mathematical, a probability density. That's one, if you've ever taken a basic course in statistics, you've run across before and were told that the math behind it was a little bit beyond the scope of the course. Unfortunately, the math behind it's a little bit beyond the scope of this one. But if you are familiar with a normal distribution and using z-scores to find positions in the normal distribution and calculate the area under the curve in order to calculate the probability that a random score is going to fall within that region. Well, that sounds very much like a calculus kind of thing. Right. Unfortunately, the normal distribution, the mathematical curve for it is known as the Gaussian, and it involves exponential functions, which we haven't talked about yet. So actually using that particular density distribution is not going to work. But in general, this is an idea that we can look at, we can think about, and we can build up. As always, when we start talking about calculus, the thing of interest is that we no longer have to restrict ourselves to constant densities, right? Talking about the styrofoam peanut in a glass of water. Styrofoam is less dense than water, so it floats. But what if you have styrofoam that you crush into a small ball? You can change the density by crushing part of it. And now the density is no longer uniform. And that's where calculus can come in and become more valuable. So let me get my head out of the way and let's take a look. Let's look at a probability example. Let's consider a coin, which is allowed to roll down a ramp and along a short track. By experiment, the probability that the coin travels x inches is given by p of x equals 1/5 minus 1 over 50 times x. All right. So thinking about this situation, we can envision some sort of ramp that leads onto a track, and we can think about a coin that is rolling down the ramp, down the track, and eventually falls over and stumbles to a stop. Now, the thing about a probability distribution is that as it's stated, it doesn't give us all that much granularity, right? Thinking about the probability that the coin rolls down this track and travels exactly, say, 7 inches is vanishingly small because there is so much precision available, right? When I say the coin travels 7 inches, do I mean to the nearest whole inch, to the nearest half of an inch, to the nearest quarter of an inch, to the nearest hundredth of an inch, to the nearest micron, 1/1000th of an inch? There's um, enough detail there that thinking about trying to evaluate this function doesn't make sense. Instead, when we talk about a probability, we're generally going to talk about a region. So a question might ask something like, what is the probability that a coin travels between 5.75 and 6.25 inches before stopping? That's something that's a little bit more reasonable. We are saying that based on our measuring devices, we have this window here marked between 5.75 and 6.25, right? I'm going to guess that we're marked every half inch. So this is the stripe that is the coin traveled 6 inches. Now that is something that we can figure out. In order to calculate the probability of falling in that region, we want to add together the probability of landing at every infinitesimal point on that region. Take them all, add them all together, see what we get. That will give us the probability. All right, taking each individual point and adding them all together, infinitesimally small, that's a job for the integral. And so that's what I'm going to do. I will set this up as the probability is equal to the integral from the lowest point, 5.75, to the highest point, 6.25, of our function, 1/5 minus 1 over 50 times x dx. And as far as performing integrations, this one is not too bad, although it is a little bit annoying because we have some decimal numbers involved. But we're going to take 1/5, integral of that is going to be 1/5 x. Integral on x is 1/2 x squared, so that's going to all told be 1 over 100 times x squared. And we'll evaluate this at 5.75 and at 6.25. All right, my calculator tells me that 1/5 of 6.25 is 1.25. And 1/100th of 6.25 squared is 0.390625. My calculator also tells me that 1/5 of 5.75 is 1.15, and that 1/100th of 5.75 squared is 0.330625. Right. Normally, I would start to round when numbers get this big, but that actually is the exact value. That's all of the digits, not just the digits on my calculator screen. So, why not write them all down? And then it's just a matter of crunching this. So we've got 1.25 minus 0.390625 minus 1.15, and then a minus is plus 0.330625. My calculator tells me that comes out at 0.04 or 4%. Right? So there is a 4% probability that this object falls into this region. Let's wrap up with a problem like that for you to try. The probability that X measured in hundreds contestants finish the obstacle course within the time limit is given by P of X equals 2/9 minus 2 square root of X over 27. I want to know what is the probability that something between 125 and 150 contestants finish in this particular run of the obstacle course. Before I set you loose, I want to remind you that X is measured in hundreds. So 125 is X equals 1.25, and 150 is X equals 1.5. Right, that's an easy thing to get hung up on, so I wanted to make sure that that was clear here as we start off. Otherwise, you're going to end up with a hideous negative number. All right, so take a couple of minutes, see what you can come up with on that problem, and I'll see you in the next video.